In this video, we are going to review the power rule. The constant rule is something we're going to look at after we look back at the power rule. So the power rule is just a way for us to differentiate so that we don't need to rely on the definition of the derivative every time we want to find a derivative, because that's a lengthy process and not always efficient. So what the power rule tells us is if you have a function f of x equals c times x to the n power, so some coefficient multiplying x, x raised to the nth power, c is some real number, n is a rational number, what the derivative will be, f prime of x, will always come out to be n times c times x to the n minus 1. So let's just talk about what happened there. The exponent of n, to find the derivative, the power rule says you can take that power, bring it down, and multiply it with what's in front. So let me just rewrite that here. So that's where the n times c comes from. Then you take the original power and you subtract 1. So we end up with this derivative, nc times x to the n minus 1 power. And that is the power rule and how you can more efficiently take the derivative of a function. So now let's look at a few examples. In number 5, the original function is x to the third. So if I want to find the derivative, f prime of x, what I would do is I would take that 3, bring it down in front. The only coefficient here is a 1, so it's just going to be 3 times 1, which is 3. And then subtract 1 from that power to get the function 3x squared. So my original function f of x is x to the third. The derivative function would be 3x squared. Now let's look at number 6. Number 6 is not as obvious because it's not written in this format, f of x equals c times x to a power. It's actually written in radical form. So what I want to do is rewrite this. Rational exponents come from the power over the root. So x to the 1/3 is equivalent to the cubed root of x. So now I know the derivative here, g prime of x, would have a 1/3 in front. That power would be brought down. And then subtract 1. Now, we talked about in class how if you're subtracting 1, because you have a denominator of 3, let's use an equivalent form of 1, like 3 over 3. Because now I know the exponent is going to be negative 2/3. And to be in complete simplest form, you want all exponents to be positive integers. So I'm going to take that x, bring it down into the denominator with 3 to rewrite this as 2/3, positive now instead of negative. And I'm still not done because I said to be in complete simplest form, you want your exponents to be positive integers. So that's still not an integer. So that means I need to go from fractional exponent form back to radical form. So power over root, the root would be 3, x would have a power of 2. This would be the complete final answer to the derivative of function g. Now let's look at function y in number 7. So y prime, before I start thinking about that, again, this is not written in the format f of x equals some constant times x to the nth power. X is not the base right now, it's stuck in the denominator. So I want to rewrite this as x to the negative 2 by bringing x out of the denominator. And now I can find y prime. I don't need function notation there, I could just use y prime. Bring down the negative 2 in front and subtract 1 from negative 2. So now I'm going to have a negative 3 exponent. And I don't want to leave anything with a negative exponent, so I'm going to bring x down into the denominator and make that a positive 3. That would be the derivative function for 7. And then if I look at 8 again, I would want to take x out from the denominator. The 5 over 2 would stay, and then x would come up and become x to the negative third. By bringing it out of the denominator into the numerator, I'd have to change the sign of its power. So now the negative 3 is going to come down in front and multiply with that 5 over 2. So negative 3 times 5 over 2 would be negative 15 over 2. And then if I subtract 1 from negative 3, I get negative 4. And then same thing here, I don't want to leave my power negative, so negative 15 over 2 times x to the 4th, positive 4 now, that would be my derivative. So that's the power rule. Let's just see how it can apply to help us with the constant rule. So if I have a constant, what it says here is if my original function is just f of x equals some constant, the derivative is 0. Now we can prove that kind of using the power rule. So if my original function is just y equals 7, let's think about putting an x next to it. If I wrote 7 times x to the 0, anything to the 0 is equal to 1, except 0 itself. That would just be 0. So if x to the 0 is 1, 7 times x to the 0 is technically still 7. 7 times 1 is 7. But the benefit of looking at it like this is that now I could use the power rule and say, let's bring that down in front. Well, then what's going to happen? I'm going to have 0 times 7. Technically, I guess I would have x to the negative 1 if I subtracted 1. But whatever this is, doesn't matter because I'm multiplying it all by 0. So this whole thing would just become 0. If you applied this same understanding to any constant, you're always going to end up with 0. So anytime your function is a constant, the derivative is going to be 0. Now this looks a little more complicated, but pi squared, that's just the number. K, they tell me, is a constant. So this whole thing is a constant, which means the derivative is 0. And then the only other thing I wanted to review from these differentiation rules was the fact that the power rule can be used if you have multiple terms in a function. So if you look back at 5 through 8, all of our functions here had one term. But even if I add and subtract terms together, as long as each term is differentiable functions on their own, meaning x to the third, I could use the power rule on its own, negative 4x, positive 5, then even though I'm adding and subtracting them together, I can still take the derivative of each term, and then each term's derivative together would be the derivative of the overall function. So let me show you how that would work. So f prime of x would be my first term, x to the third. I would bring the 3 down in front and subtract 1 from the power. So that term, the derivative would be 3x squared. Then for minus 4x, I'd bring the 1 down in front. And then if I subtract 1 from 1, I would only be left with 0. X to the 0 is just 1, so I don't really need to write that. And the derivative of 5, that's a constant, would just be 0. So really, I could simplify this derivative by just saying f prime of x is 3x squared minus 4. And let's just try one more. For number 10, g prime of x, the only thing I might do over here with my original function is rewrite that first term's coefficient as negative 1/2. It's always nice to see x as its own unique factor, not stuck in a fraction. So I'm going to bring that 4 down and multiply it with negative 1/2. 4 times negative 1/2 is negative 2. Subtract 1 from 4 to get a new power of 3. Bring that 3 down to multiply with 3 to give me a 9. Subtract 1, I get 9x squared. And then for this last term, bring the 1 down in front, multiply with the 2, then subtract 1. I would technically get x to the 0, but we already know x to the 0 is just going to give us a factor of 1, which we do not need to write. So that would be the derivative function of g and f using the sum and difference, which again just allows me to use the power rule with multiple terms in a function. I hope this video helped review the power rule and how it can apply to multiple terms and constants.